All right, welcome back. And as mentioned, we covered the equations of motion. Now we're going to look at some boundary layer thickness in your packet. So here we are back in inhomogeneous turbulence and modeling. And there's a pretty famous paper written in 1954 by one Klebanov. And he looked at some of these balances of the terms in the energy equation, which we were mentioning previously for low speed turbulent boundary layers. And here's one interesting plot of his work. Here's the wall. Flow goes from left to right, as you know. And he plotted this mean velocity profile. That's what you're seeing here. So of course, here's 0. Here's u infinity. And this is the x direction, y direction. So this is all pretty standard. And kind of taking snapshots and having human computers, which have been replaced by machine learning today, right, for visualization, he looked at where the boundary is between the turbulent flow and what people saw as the potential flow. So out here in this region, this would be the potential flow, and this would be the turbulent flow. And it's just colored in with a granulation. But along here, there's some boundary, which you see, which divides the region of turbulence, which the region of like a laminar potential flow. And we also defined previously boundary layer thickness delta, right, which delta is on the order of 0.99 u infinity. That's a distance in, say, meters from the wall. It's meters. And what's interesting also about this particular photo is you'll notice that the mean position, that is, if we take this blue line and average it, and we take like, millions of snapshots if you could, in this case maybe 1,000 of a steady flow, a turbulent flow, statistically stationary, then you would find actually the mean position is about 80% of delta for low speed flows. So that's interesting. And sometimes you can see that this region of potential flow is all the way inside what you would see as the boundary layer. So this is normal that this front between the turbulence and the potential flow is so different. Okay, so we're going to pull two equations. The first in 3.3, and I didn't have a 3.1 or 3.2, because I actually have maybe 4 pages of just general introduction for this chapter, but we kind of already talked about them, so I decided to save time and skip that. But these are nothing but taking the energy equation for fluctuating velocities and writing it in these ways. Well, the first is mean kinetic energy equation, and that's operating on u squared, right? So that's a term for kinetic energy, essentially. And here's the turbulent kinetic energy term with the trace. And here Q is our TKE. And you see I've already dumped some terms. We are turbulent. We're statistically stationary. And it looks like we're incompressible. And I notice in these equations that we've dropped the bars for mean quantities. So here, these fluctuating quantities, like a prime, right, that's fluctuating. And the bars, the correlation term or average, and terms like, say, u itself, right, that would imply like it's an average term. So this is TKE, and that's the mean kinetic energy of the flows. Okay, some quick notes about this. The mean dissipation term, which would be mu of partial u partial y squared, is not in equation 3.3. We dropped it as we're incompressible. And I'll just write incomp. And it's just small compared to the rest of the terms for low speed incompressible flows. It's much less than other terms. So there's a first nice simplification and assumption, and it's done based on experimental observation. And this turbulent dissipation term, phi, and the two viscous terms, which are, looking at this equation, it's going to be partial y of u of mu of partial u partial y, and one involving v of partial 2 partial y squared of q squared bar over 2 plus v squared bar. In these equations, 3.3 and 3.4 are going to be small outside the viscous sublayer, which isn't very turbulent. So for modeling purposes, we're also going to neglect them. So right, neglect as they are small outside the sublayer. Just write that because I can save a little bit of time. So put it there. So if I make this assumption that they're kind of small outside the sublayer, then I'll have to restrict our cross-stream position to be outside the viscous sublayer. And here we'll just write delta sub s as the sublayer thickness. So if we go back here, this viscous sublayer is in, I'll just highlight it, sort of this region here. Just highlighting. I should have done it in orange. This region here, very close to the wall, right? It could be 5% or less of the wall for a low-speed flow. Okay, so if I make these assumptions and I put them back in 3.3 for the mean kinetic energy and 3.4 for the turbulent kinetic energy, I'll have these two resulting terms here for mean and here for TKE. So once again, this is a TKE, and this is the mean term of the whole velocity. So here, I'm going to make some notes, and we'll go look at the figures of which are on following pages. This is a LaTeX typesetting system, so it kind of has shifted things around. It's always entertaining to try and typeset LaTeX and get figures to be in the correct places. So these figures are going to show the loss of mean kinetic energy is high, except very close to the wall. And that makes a lot of sense because turbulence near the wall is small. And that's actually opposite, though, where turbulence is produced. Turbulence is produced very high and very close to the wall. And also, the kinetic energy lost by the mean flow in the outer region is transferred by the working of the mean flow against the Reynolds stress to the inner layer. It would be very hard to discover these things without computers doing DNS, so these were observed experimentally. So let's go look at figure 3.7a down here in our notes. Here it is. And you'll see in 3.7a, the caption is the balance of kinetic energy in the mean flow in the boundary layer, zero pressure gradient boundary layer, according to the mean kinetic energy equation from the experimental data of Klebanov. So here, he's taken that reduced equation and experimentally, not directly measure, but experimentally estimate what these three terms are. One is convection, which is the movement of the property of mean kinetic energy right there. There's the work done by the shear stress, and of course here's production. So all these are the same type of graphs. Here's the wall, right, wall edge, and here's the edge of the boundary layer at 1. Right, so delta is here, y over delta equals 1, that's the boundary layer edge, once again. And the way we plot these, it turns out, it's just like airfoil coordinates for lift distributions. We would write, basically because of the negative signs, the negative sign means it's like a positive gain of turbulent production. So let's look at these little convective term first. That's the circle, so that's this line. And so most of, you could say the turbulent convection is happening in the middle. That's a log region. And then we have work done. Those are the squares. That's this line. And we'll do one more. Here's the energy turbulent production. triangles, and most of it happens, you can see, near the wall, which is very interesting. Most of the mixing actually happens in the middle of the boundary layer, and we'll see that in this class too. Okay, and what do you see if you take any particular position, like here? If we sum the terms, it should be equal to 0, of course, at any cross-stream direction. And that makes a lot of sense, because if we go back and compare it to the equation that was developed here, these terms, it's of course equal to 0. So if you were an experimentalist, that means you would only have to say, how can I estimate 2 of the terms accurately? And then I would just add them and multiply by -1 and plot that. And that's exactly what Klebanov did. He also do that for the turbulent kinetic energy equation, which is plotted in 3.7b. But now there's 4 terms for TKE and an incompressible boundary layer. And let's look at them just to look at a little bit about the physics. So in these plots, there's an inner region close to the wall, right, and an outer region far away from this equation. And here, the production of turbulent kinetic energy is due to this Reynolds stress term. And there's the Reynolds stress. And just to remind you, this is normalized U sub t or U sub tau, depending on me not hitting the right key, is of course friction velocity, just to normalize it. So before we look at the plot, just like the other one, let's make a few notes. We'll observe that the contributions of total energy balance are equal and opposite. And the flow in the inner region is governed physically, if you will, by local conditions. And that's opposite of the outer region of the boundary layer, where the terms are governed or need to be modeled by, say, 2-point correlations. And this is informally what people call like the memory of turbulence. A few other things. In this flows, we'll see in a second that the fluctuations of U in middle and outer region is very strong. I'll let you just finish copying that for a second. Oh, and one other thing I should note, in my notes too, is that there's strong intermittency at the boundary layer edge. Can anybody recall what the physical property of intermittency is? Maybe you saw that through your Lorentz predictions too. There's periodic or semi-periodic or chaotic events that are kind of unpredictable, and they have very strong tendencies to maybe have like a small little blow up or fluctuation that's not expected. So let's go look at this particular figure again down here. So this is the second one. So we have 4 terms once again, the same y-axis, right? So from y, delta is the boundary layer thickness right here. But you know, because of these large turbulent eddies at the edge of the boundary, they're like extending out into the flow field, and also you might have large regions of potential flow below delta. It's the same type of graph. So here we have production, but this time it's the production. This is where the energy is created, right, due to the interaction of the mean flow with the mean flow, or the mean flow with the turbulence, or the turbulence with the turbulence. So there's production, and it's right here. And I should note, and I noted it on my own notes too, that this is the outer coordinate, and this is the inner coordinate. So they've plotted both, or Klabanoff did. What else? This energy dissipates into heat. There's no acoustics, but it's in compressible flow, and those are the circles. So you can see through most of the inner layer, the production and dissipation very close to the wall is dominant. And the two other terms, convection and diffusion, are just negligible. That's interesting. And in the outer coordinates, there's a lot more variation. But you can see further away from the wall, the convection diffusion equations. The bottom line is these are balanced near the wall. Production and dissipation energy is dominant in the terms. Farther away from the wall, you do have to worry a lot about the convection and diffusion terms. Okay, so let's go back to my notes. Oh, that's what I wanted to cover there. Okay. So let's look at some of these graphs. And I want to talk about these in terms of figures. And we'll just discuss these. So I took 4 pictures produced. I think these were produced by a series of experiments here by Runstadler. So I don't know who this person is, but these pictures were compiled by Cebeci, who is a turbulence researcher. We'll talk about his model later. And he's looking at 4 bubble fields. So how was this experiment done to understand physics of the turbulence with the composite profile and look at fluctuations? Well, he had a flat plate with a 0 pressure gradient. So there's your flat plate. And I'll just draw a profile quick like that. And this profile here, of course, corresponds to this graph. So this is the wall region right there. And out here, there's the outer region right here. And once again, we have the viscous sublayer, which would be written as the subregion. That's this region here. Then there's the log layer, or he writes the fully turbulent region, and then there's the outer region, or Coles region, which is the wake region. So this line here, once again, is the log law of the wall. This area here goes as y plus, goes as u plus, and this is the Coles wake region. Okay, and you can see right here, here's the log law of the wall drawn by that dotted line. And he just uses the coefficients near 5, he set it to 4.9 to fit well. Okay, so now in his experiment, he basically put a wire. And the wire, if you're looking downstream of the plate, like into the board, like this, he put the wire here. And when you run current through it, little bubbles form on the wire, and they fall off the wire and go downstream. It's a bubble wire type experiment. These were done and are very popular. In fact, they were used even when I was an undergrad, and I did bubble wire experiments at Michigan State in the fluid dynamics lab for a short time. Anyway, he puts this wire here, and if you're looking in this direction, it'd be right here into the board. So you're looking into the paper from this viewpoint, and the little bubbles come off. And then he put a camera like this that looks down, and he takes snapshots. And that's what these pictures are. So in this case, here's the wire, and the flow is going downstream. And in these 4 images, he also had a hot wire, which is downstream, located at like this location. So you can see from top to bottom, you're going left to right in this figure, and top to bottom of the flow in this figure, and you put this hot wire downstream in this location. Okay, so that's the experimental setup. So what does that physically mean? Let's look at that. Well, in this case, each of these figures, he's labeling an arrow. So this is the distance from the wall for this figure, which is about y plus of about 500, and it's in the wake region. Okay, this is the plot, and you can see before the age of computers, they had a little line plot, and don't ask me exactly how it's done. It's beyond me. I'm not an experimentalist. I didn't work with experiments that didn't use digital computers. But here's the velocity in feet per second. It's only going about 0.4 feet per second. And you can see this is the turbulent, well, this is the total velocity actually. If I wanted to find the fluctuating velocity, of course, I'd take the average and I could find u prime. So you can see there's very little variation. And therefore what? Very little turbulent kinetic energy. And you can see the bubbles, they're interesting. So what you're actually seeing sort of like lines of these bubbles because the wire wasn't just turned on, it was pulsed. And that way each pulse can be timed and you can see how far downstream these little bubbles convect in the turbulent boundary layer, at 1 second intervals. So actually each one of these little things between each of these is about 1 second on the graph. And this is scale in inches, of course. Okay, so looking at all that, you can see things are pretty normal. Generally a straight convection speed, but downstream you can kind of trace that these lines have become a little bit offset. So what does that mean? This is really the cross stream direction, right? If you're looking from the side, which is normally what we do. And this probably means that there's different convection speed of the turbulence, in the outer part of the layer. Anyway, I think it's very interesting that you can start to get a physical picture of what these boundary layers look like with these basic experiments. So here's another one. And he just moved the probe position here ever so slightly down. It almost looks like the same picture. In fact, in my caption here, which I copied from his paper, says B, y is 2.5 inches. So he moved it down only 0.75 inches. But of course, in the log coordinate, it almost appears in the same place. You're still in this wake region right here. So look at the velocity fluctuations. Just for the human eye, you can see it's gone down a little bit, so the average has gone a tiny bit down, which makes sense because this is u plus, so this is a log coordinate too. And it's a slight bit, but it's gone down maybe to 0.38 feet per second. And the amount of variance has increased slightly. But look at the structure of the turbulent boundary layer in this case. So here's your wire again, and we can trace lines of the bubble location along the wire with increasing time. But now, in this case, even slightly down, we're getting strong turbulent eddies. And it's a huge change over just a tiny little distance of y plus. Let's look at two other probe locations. And this one now, you can see this is in the log layer. And there, the turbulence is in some sort of equilibrium. The turbulence is not in an equilibrium truly in the outer part of the layer because of these large intermittency factors. The large eddies are entraining and reaching out far into the ambient fluid. Here, this is considered a place where the terms in both the mean and turbulent kinetic energy equations, which we just showed, are in balance. And you can see that from the previous graphs I showed, right? Okay, so that's cool. And you can see now the mean velocity u bar has gone down to about, 0.25 feet per second. And there's way more variation in the signal, right? So there's way more turbulence, or TKE in this case, even though we have a lower mean kinetic energy. And now let's look at our bubble field. And that's in the log layer. And I have to tell you, I find the picture to be very aesthetic. And anyway, so here's the wire. And you can see just downstream, things are starting to break up a little bit. And then further downstream, you can see that there's large vortical structures and turbulent eddies. And this is just my guess of where the line would be. There's no way to draw it, really. And further downstream, the turbulence might have totally removed some of these eddies. In fact, for this experiment, for this amount of time, they haven't even reached the bottom of the graph. So here's maybe the furthest reaching set of bubbles right there, this location here. Okay. All right, there's one more. If you're considering, hey, what happens closer to the wall in this interesting experiment. And you say, well, okay, I did 2 probes in the outer layer. I did a probe in the log layer, and they all look pretty similar. What happens when I put my probe near the wall in the wall region? That's what's happening right here. So now you can see, oh, the turbulent fluctuations are even higher. And this is really at the edge of it, right? So usually this viscous sublayer is kind of in this region. And you start to getting to this region about y plus 9, 10, 11, and you still get large turbulent fluctuations. But down here, if my probe was next to the wall or very close to the wall, it should look like a laminar type flow. Very low U bar and almost negligible turbulent fluctuations. Very, very small. Anyway, you can imagine if I put a line through here, that'd be the mean flow. I'm all the way down to 0.135 feet per second. That's relative to about 0.22. And large variation. And now look at my turbulent boundary layer. Here's time 0. Here's time about 1 second there. And downstream, these things have become long streaks. So those are the streaking you would see in a lot of these turbulent boundary layers. And if you look at DNS simulations, like you can go on different researchers' websites, you know, DNS on YouTube of turbulent boundary layers for low-speed flow, they make these types of graphs and can visualize them. But these set of experiments were remarkable because in the 1940s, a lot of the early turbulence models always assumed that all the energy was in equilibrium in different parts of the boundary layer. But these types of experiments showed it wasn't true. And in fact, they were also really surprising to people to see these long, coherent streaks of turbulence because people even argued that they wouldn't exist. And so these kinds of experiments were just, I think, amazing to the people at the time because it probably told them that a lot of their early theories weren't correct. So those are some of the things I wanted to sort of note about the early turbulent boundary layer work. And now we can move into the early ideas of modeling. So we have our equations, we have a basic type of flow we want to model, and now we're going to try and just talk about some of the thinking and arguments, the physical arguments based on these observations to try and close those complicated RANS-based equations. So what's our objective? Ultimately, we want to predict useful things for the benefit of individuals in society, like drag and lift. And to do that, I probably need to know, say, derivatives, like partial U, partial Y at the wall, pressure at the wall. And to get those quantities in a turbulent flow, I had to do averaging and simplification in the equations, and I need to close them. And I can only close them based on like physical observation and analytical theory. And today, if I have DNS database and machine learning, maybe that's part of the future and what people are also using today. So the early concepts were coming out in the late 1800s and by Prandtl's group in Germany in the early 1900s. And this is a sentence here, which is basically noting what I just kind of told you, that we're looking for mean velocity distributions and maybe temperatures, pressures throughout the turbulent boundary layer, because that's what creates an incredible amount of drag, skin friction on the vehicle, right? So ultimately you want to seek like skin friction and pressure on the vehicle. And the first models were called Eddy Viscosity models, which you should see from the title. And it turns out that many of the other models proposed, or even more complicated models, would reduce to an eddy viscosity approximation anyway. So these are most popular models even today. And most of the RANS closures and CFD models, in my opinion, still fall into these categories. So what's new in the world? Some things, but not as much as we would like. And of course, they do lack some kind of generality. We might calibrate them for a turbulent boundary layer, but they may not apply to other flows. And one of the things that's a problem with these types of models as they're originally formulated is they're based on the idea that things have to be in equilibrium, or at least local equilibrium. So when we're looking at these graphs at the boundary layer, you notice what? That things, at least the equations, are not in equilibrium in the outer layer, and but we're formulating and calibrating our models, like say in the log layer, where things are in equilibrium. So the core idea is that we will look at the rate of change of the Reynolds stress in the governing equations, which is key. And these are referred to the transport equation methods. Hear those words. And even if you look at Reynolds stress models, some of them, if they're in equilibrium, would reduce to eddy viscosity models. So who was the first to propose this idea that in a turbulent flow is like just another medium of matter, in a sense, and that it would have a different viscosity? Well, that was none other than Boussinesq in 1877. He's credited to kind of proposing this first type of model and to try and close the boundary layer equations, the turbulent boundary layer equations. So what did he propose exactly? He assumed that the turbulent stresses act like viscous stresses, which implies that the turbulent stresses are proportional to a velocity gradient. Okay, so if turbulent stresses are proportional to some mean velocity gradient, that means that to have turbulent production in a flow, I would have to have a mean velocity gradient. Immediately, I can think of flows that are turbulent, which have no mean velocity whatsoever, or even no mean velocity gradient locally. For example, I could just have a room, and I close the doors, and have HVAC, seal up the HVAC. And I go in the room and I just wave my hands around and wait. There's going to be no mean velocity because there's no real flow. But there are turbulent fluctuations. So immediately you see there's problems with this model. And those problems are what Prandtl noticed, and he'll introduce a new form. But in this case, this is where the core and original idea of eddy viscosity came from Boussinesq. And he, I believe in his paper, he wrote it as epsilon sub m, so we'll use that. And so what does this equation mean? This is his original statement. And he said the Reynolds stresses, which are rho u prime v prime in this case, there's not going to do a w prime in the model, just to close the model as simple as possible, goes as the density times the eddy viscosity times the velocity gradient in the flow. So that's partial u partial y, which certainly exists in a boundary layer. When you're outside the boundary layer, partial u partial y is 0. So there would be no Reynolds stress, which is good. You can see it's such a simple differential equation. What's also interesting about this equation is that, in the model, you might say mu plus epsilon m. So effectively, epsilon m is added into the viscosity in the original momentum equation. So this is your extra equation. This is the basically a one equation, simple model. Okay, now you say, well, what should epsilon m be? I just wrote it down. Well, I know it should have a certain number of dimensions, right? And what would the dimensions be? Well, I know the dimensions on the left-hand side of the equation, and the dimensions on the left-hand side of the equation should be proportional to the right. So I have density and density. Okay, so those would kind of like cross out. So now I say, well, epsilon m times partial u partial y should be proportional to v prime u prime. So that should be something like a length times a velocity. And you can see that would be something like meters times meters squared per second, which gives me meters, is that right? Nope, that's not meters. It's meters per second, excuse me. Meters squared per second, so that's like a viscosity. And then this term here, what is that? Partial u, partial y. That goes meters per second, and it's a derivative with respect to space. So that's a per second term. And then that balances over here with a meter squared per second squared, because that's an energy, right? So I think that works out. So that's the core idea. But this choice here, I think that was hard to make, especially without a wide range of experiments. So now the big problem is that Boussinesq and others were thinking is like, well, I know this little eddy viscosity term, which modifies the flow by making it more viscous. That's the effect of turbulence, essentially, in the idea. What would I choose for length and velocity scales? And there can be a lot of arguments about that. Some people say, well, according to the kinetic theory of gases, and this was pulled from a paper in 1938, the viscosity itself should go as a constant times a mean free path, which is lambda, and the speed of the molecules. And this is a molecular argument. You know, it's not based on turbulence. Turbulence is a continuum phenomena. So you might have little points, and the mean distance between them is lambda, and the speed of each of these little guys, lambda is the average collision distance, right? That's mean free path, and c bar is the speed, average speed of these particles. Okay. Well, that's nice. But in this equation, 3,7, and I note here that the turbulence is really macroscopic properties. They're larger and much larger scales than the microscopic molecular scales of motion. And there's some little observations we should make to maybe make a better model, or even relate it to the gas theory. So we note that the fluid, it sort of resides in eddies, turbulent eddies. Yeah, sorry about that. And they're macroscopic. And they move at, say, u bar, something like that, or at least go as u bar, or at least some fraction of it, we know. But they also lose their individuality at a small time. And they also travel some distance. And they also have a size. So their distance traveled might go as u bar, which is a velocity scale, and they might also have some size, which is sort of like a length scale. So these might be clues of what we might write our eddy viscosity as. So using these ideas, maybe we can write our eddy viscosity as some length scale, and I'll write that L. And maybe some, once again, velocity scale, I might write V prime. So here, V prime might be the velocity of the eddies, and L is their integral length scale. And, you know, we can choose anything. We could set L as a constant, like maybe in a turbulent flow, all the length scales are a constant. That would be one assumption, but probably a bad one, because we know that turbulence is consisting of all kinds of different eddies, and they also have all kinds of velocities. So these shouldn't be constants themselves. So let's look at some more properties, a little observations about this. We note that turbulent motion is maintained when well, I'm not sure how I want to write this. Maybe, hold on a second. I don't like that statement. back. Yeah. Sorry. Okay, we note the turbulence is maintained in motion in boundary layers. But also you could have U bar goes to 0. You still have L and V prime are non-zero. So just using like the Boussinesq idea alone, that original equation, 3.7, may not be appropriate. And that's sort of like the example I just gave, that you could have a homogeneous isotropic turbulence that has fluctuations but no mean velocities. So you can't really close systems with a Boussinesq original approximation. It's not as general as we would like. So this is where Ludwig-Prandtl came in, right here, after his 1900 boundary layer paper. And he proposed what we know today as the mixing length theorem. And I'll write it out for you. So Prandtl, using some arguments, which I'll discuss in a second, wrote that the negative density of the Reynolds stress, to close the equations, goes as rho times a length scale squared times the magnitude of partial u partial y times partial u partial y. So this is another model where, of course, if the flow goes to 0, you might still have fluctuations in Reynolds stress. So it's only applicable to boundary layers. But there's some arguments in here of writing the model this way relative to Boussinesq's way that made it very popular. The first thing I would like to note is that there's no clearly defined distances between the particles, of course. And there's something introduced called a momentum deficiency, which is rho u, or rho L partial u partial y. And another thing you might notice from the continuity equation is that the vertical velocity is proportional to v prime in the boundary layer, and therefore v prime should go as u prime, or at least be proportional to it in some way with a constant in the region of balance in the log layer. And this is graphed up here in this little chart I found from a really old book. And here is u, and here is v. There's one position, and they just sort of graphed a relation with u of y for v prime and u prime. So for the continuity equation to hold with fluctuating velocities u prime and v prime, they have to be equal or proportional and opposite. And that's what's written here. Okay. And it's 1:40, so I think we'll take a break here and kind of try and keep developing our eddy viscosity model from Prandtl on Tuesday. So thanks for your time.